How would you read it? X root y is what we would read, right? Okay. Now, what math is happening right there? Multiplication, right? Between the two. You've seen this before. If I write x, y, how do you read that to me? X times y. When there's no operation written, it's times. We know this, yeah? Okay. The x is anybody remember the fancy word for it? It is a variable. You're right. That was silly of me. That particular location has a name in math. Does anybody remember what it is? It's a coefficient. Okay? The y is what we call an argument. Because the y is going to change what happens to the x, right? So x is a coefficient, y is an argument. And we know that coefficients multiply by an argument. Now, what if I gave you this? 2 times 4x. Don't write that down. What do I have there? That's from the 9th grade. We're going to be reviewing that in the next unit before we go on to the grade 10 level of polynomials. But this is from the 9th grade. What do I have there? If there was no x, what would I have? 2 times 4, which is 8. So when there's an x there, what do I have? 8x. Everybody cool? We all remember that from grade 9, right? Okay. And you remembered that coefficients go with coefficients, right? Okay. All that's already in your head. So now let's apply that to grade 10. We can multiply radicals, and this is very important. They have to have the same index. Much like we have to have the same base to multiply exponents. We have to have the same index here. So I can do square root of x times square root of y. That's okay. But I can't do square root of x times cube root of y. That's not okay. Everybody cool? All right. So again, let's write it out. X root y times a root b. So I have two things here. Can I multiply them together? Yes. Why? Because they have the same index. But there is no index written there. Aha! That's okay. We know it's 2. So, remember, coefficients go with coefficients. So the answer to this is x times a, and then arguments with arguments. Root y times b. That's all you do. But again, as always, what do we always do at the end of every question? We simplify. Everybody cool? All right. So it starts so easy, it's almost embarrassing. What is the negative 7 going to multiply with? The 5. What is that? So I'm going to write it all out for these first two. Yeah? Obviously, we don't need to forever. So I'm going to have negative 7 times 5. Then I get my square root. And what's going under there? 3 times 8. What is negative 7 times 5? Negative 35. Root. What is 3 times 8? 24. And then, if possible, I simplify. Can I simplify the root of 24? Can I? I can do 4 and 6. Why did I choose 4 and 6 instead of 8 and 3? Because 4's got a perfect square, right? Out comes what? 2. What's 2 times negative 35? Negative 70 root, and what did I leave under there? The 6. And we're done. Everybody cool? It's pretty easy, right? Okay. What isn't written there that is there? 1. So I do 1 times 3. What's that? 3 root. What's 2 times 8? 16. Can I simplify 16? What is it? It's 4 times 4. It's already a perfect square. So what comes out? 4. What did I leave under there? So what's the answer? 4 times 3, which is what? 12. Everybody see how easy this is? There's nothing going on here that's complex. So you should all be able to do C and D, right? After you're finished D, I'm going to talk to you a little bit. You go ahead and do C and D. It'll take you like 30 seconds each. I get that. It's cool. Go ahead. I, of course, am going to write it out the longest possible way. Now, everybody's cool, right? Not complicated. Everyone's good. Numbers getting a little bigger. Maybe you needed to use your calculator to do 48 times 6, but that's okay. We're all good, yeah? All right. I've highlighted this because this is a really important thing that you can see quite right plainly. When I multiply root 3 times root 3, I end up with root 9, yes? Right? We just proved that. What is the root of 9? 3. So that's a pretty big thing that happens in math that you are aware of. Because of course, if it happens once in math, how often does it happen? Always. So what if I had the root of x times the root of x? What would the answer be? It would be the root of x squared because of exponent laws. And the root of x squared is what? X times x, so out comes an x, right? So it's x. So please notice, if I square a radicand, the answer is the radicand. Is everybody cool with that? Like, if I were, for example, don't write this down, to do the square root of 5 times the square root of 5, that would be the square root of 25, which would equal 5. Root 5, 5. Everybody good? You have to be careful with that. It's going to be very useful to you in further math classes. But if you're not paying attention to what's actually going on, if you forget this part, that it's root 25, then the next thing I write is going to screw you up. Don't write this down again. Just use your brain and think about it. Cubed root of 8 times the cube root of 8. What should the answer be? If you've just followed this shortcut, some of you will say it's going to be 8, right? Because, root, you get the radicand. But the real path you're supposed to follow is this one, right? So this would be the cubed root of, what's 8 times 8? 64, and the cubed root of 64 is 4. Everybody understand? You can't just say, if I put two radicands together that are the same, I'm going to get that. Because you're not. Everybody understand this? What would I have to write right there if I wanted this answer to be 8? Yes, there would have to be a 2 there. Because then I would have 8 and 2 more 8s. I would have the cubed root of 8 cubed, which would then be 8. Does everybody understand? Not incredibly important yet, but a pretty darn big deal very soon to get rid of radicals. Yeah? Okay. All right. Now that we're comfortable, because everybody looks comfortable, everyone's nodding, saying, yeah, okay, I got this. What do you think will happen there? It looks weird. What's weird about it? There's some adding and subtracting, yeah? Now, if none of this were there, would you know what to do? What would it be? What would this be? 5 times 3, which is 15, root what? 16. Everybody cool? Easy peasy, right? Okay. Now none of that's there. What's that? 10 root 24. And now none of that's there. What's that? 5? Negative 5 root 40. Plus, minus. See, you all knew how to do it. Is that the answer? No, why not? Because I can simplify it. What is the square root of 16? 4. So what's coming out? What's 4 times 15? 60. Does 24 simplify? To what? We've already done 24 on this page. 6 times 4, thank you, Prab. Why'd you choose 6 and 4 instead of 8 and 3 or 2 and 12? Yes, 4 is a perfect square, so what's coming out? So what's that become? 20 root what? 6. Does 40 break down? 4 times 10. Why'd you choose 4 times 10 instead of 8 times 5? Perfect square. What's coming out? So what's that become? Negative 10 root 10. Am I done? I haven't actually taught you this. Do you think we're done? Can we simplify some more? 6 is 2 times 3. Any pairs? No. 10 is 2 times 5. Any pairs? Okay, so we can't simplify there. Now, the only thing you think we might be able to do is maybe we can add those, right? Maybe. Well, let's think about that for a second. 20 root 6 would be, if we were writing it as a coefficient and a variable, it would be 20 times x, right? We all agree? Same thing. Everybody cool? Minus 10. Now, is that the same as that? So can I use x there? What would I have to use? A different letter. Can I add those? I can add x's and y's, Riley? Rylan? I can add x's and y's? Say no. Right. You can't you? So could we add these? No. What if it was 20 root 6 minus 10 root 6? Then what do you think the answer would be? 10 root 6, because I got 20 root 6's, which is the same as 20x minus 10 root 6's. Since the root 6's are the same, we could keep the x. Everybody cool? All right. Okay. Anything different in f? Is it still a radical? Is it multiplying by a radical? Are they the same index? So can I multiply the radicand times the radicand? So how many of you want it right now? Do the cube root of 16 times 54. That's what we want to do, right? Now, 16 times 54 is the cubed root of 864. That's going to be a hell of a factor tree, isn't it? It's not even going to be a factor tree. It's going to be a factor redwood, right? It's going to stretch down the whole page. Can I make it easier on myself? Sure I can. Why would I do a cube root of a giant number when I have these little numbers right here? Isn't 16 8 times 2? Why would I stop at 8 and 2? 8 has a cube root, right? And 54 is 2 times 27. Why would I stop there? 27 has a cube root. What's the cubed root of 8? 2. What's the cubed root of 27? No. 3. So out will come a 3. What did I leave under there? What did I leave? 2 squared, which is 4. So it is 6 cube root 4. Everybody cool? Now, once again, if you aren't thinking about what is actually happening, a bunch of you would have done this. Like I said, you would have gone 864. Holy crap. Okay, 2, 432. Okay, 2, 216. Okay, 2, 108. Okay, 2, 54. Okay, 2, 27. Okay, 3, 9, 3, 3. Holy crap. Well, there's a group of 3. There's a group of 3. You'll get the same answer, which is faster. Right. I know you guys. I'm teaching math for a long, long time, longer than you guys have been alive. You would much rather do work with smaller numbers, right? So do the work with smaller numbers. So let's look at the very next question. Can I do that work with smaller numbers than 28 and 63? Sure I can. What's 28? 7 and 4. What's 63? 9 and 7. What's square root of 4? Prab, you might as well finish this off because you got this. 2, what's coming out? 2, so what do I got? Root 7 times. What's square root of 9? So what's coming out? So what do I got? 9 root 7. What's 10 times 9? 90. What's root 7 times root 7? Technically, it is 7, but technically, what is it? It should be the root of what? 49. And then the root of 49 is 7. So what comes out? What's 7 times 90? What's 7 times 9? 63, and then you add a 0. And the answer's done. Easy peasy lemon squeezy, right? Nothing new mathematically today, because you already know how to simplify radicals, and you already know how to multiply. What if the numbers are big, you can't multiply it in your head? Do I care? Of course not. You get your calculator out and you do it. Right? See what your work is? Page 102 and 103. We have a quiz tomorrow. Now listen, what if you don't finish this work today? That would be silly, because I'm giving you 45 minutes. Is there any reason not to have this work done today? Of course not. Right. Two things are going to happen tomorrow. One, I'm going to give you back your quiz that you did while I was gone. We'll go over it, because quizzes don't count, right? We'll go over it. You'll see all the right answers. Also, I'm going to give you back that assignment that I gave you the second day I was gone, because you guys I missed 2 classes for. That assignment, you had no answers for it. You're supposed to hand in your work separately, yeah? Right? Now, I noticed that Mr. Fisher did some work on the board, right? I noticed there was a couple of the carpet square questions were showed up on the board and stuff like that, yeah? I'm not too worried about it. I'll give it back to you. I'll just have gone through it with ticks or X's, okay? I'm not gonna, say, oh, fix this here, fix that there. I'll give it back with a tick or an X, and then I'll go over it quickly. You can put in where you need to fix where. Got it? Everybody cool? And between that and our quiz tomorrow, that should take up most of tomorrow's class. Because the next thing we're doing is something that puts exponents together with radicals in one question. So I want to make sure everybody is good at exponents and radicals before we mash them together in one thing. Okay? Go. I'm going to take attendance.